All right, this is Vera from Stillwater. The lecture on multiprogramming from yesterday had terrible audio quality, so I'm going to redo it. So I have a good archive of the lecture. There are no students, but I have my lab mate here who's watching.
Hey.
It's Sunil, so he's my quality control. So let's get started. So today we're going to talk about multiprogramming. So what is multiprogramming? So far, how have we been executing our programs in our microprocessor? Right, so we've been actually have just a single program that the processor executes repeatedly. Right? Is this how your general purpose computers, such as your laptops, your desktops, your smartphones, is this how it works? Do you just have one thing executing all the time?
No, it has multiple programs in parallel.
Is it in parallel? What if you only have one CPU?
It's a superscalar processor, yeah.
Yeah, but still, it's one process at a time, right?
Mm-hmm.
But how do you accomplish that? How do you actually have multiple programs that seem like they're running simultaneously? How do you have a CPU that support this kind of?
You mean like by multi-threading?
Not multi-threading. Imagine you have one CPU,
okay.
Just one core.
Mm-hmm.
When you're in Windows, you can still have multiple copies of Word and Notepad,
yeah.
And you can still switch between the programs quickly. So how does it work? Like, how do you actually get these programs to look like they're running together, right? Even if you only have one CPU.
Okay.
So that's what we're going to talk about today and see how the CPU and other support stuff allow you to maintain this illusion of multiple programs running at the same time. So this is all possible because your CPU now is so fast that you have enough CPU cycles where you can accomplish this. This is called multiprogramming. It's when having too much time on your hands is a problem.
But this is assuming you still have only one CPU.
One CPU. Okay. So let's review how we've been using the CPU to execute programs, right? So if we have seen a diagram similar to this before, so you have the CPU, you have the bus that connects everything together, you have the I/O devices. Here I singled out the terminal and keyboard for the I/O devices. So this is basically just like your monitor and your keyboard input, just to have a simple I/O device for the human user, right? So you can see what CPU is outputting. You can input human readable commands, and then you have the non-volatile memory and the main memory. So the non-volatile memory is typically a flash in your CPU, in your computer, and the main memory will be your random access memory, which is which is volatile. So what it means when you power cycle it, the data within the memory is gone. So non-volatile, you can have your data survive between power cycle. So usually you put your program inside the NV memory, the non-volatile memory. Right? So this is where a program is executed when the CPU boots up. Usually this is flash or EEPROM. In many systems, these memory locations are all memory mapped, right? So the CPU can execute instructions off this read-only memory by pointing its PC at the non-volatile memory. So this is the reset or boot vector. So when the CPU boots up, it has this memory address on its PC. So to start. So when the CPU clock cycles, it starts fetching instructions from this memory location, right? So for an embedded system, so a computer with specialized function, that's it, right? You have this program, this set of instructions here in your non-volatile memory, and you just repeatedly execute those instructions to achieve whatever function that system is trying to do. For example, in this case, all it does is read values from the sensors through the analog to digital conversion, and then display what the value is. So it only does one thing, one specific thing. This is how typically an embedded system is arranged. But in your car, you have lots of small systems like this with a CPU that just does one thing. Right? Your microwave, maybe your toaster. If it's an advanced enough toaster, you might have a microcontroller. But is this how your desktop computers and your smartphones work? Just one thing? No, it does a lot of things.
Yeah.
Right? So how do you make the CPU execute multiple programs or making it multifunction? So let's go back to the 80s, back to the DOS days, and this is how DOS actually does it. Right? So you have multiple programs stored in RAM or in non-volatile memory, and you can execute either one depending on the situation. So first of all, you have your boot program. So in this case, you'll just ask the user, hey, what do you want to do? It gives a terminal interface. What do you want to do now? Like, do you want to execute program A or do you want to execute program B? Just like the DOS prompt, right? So, okay, let's say the user wants to execute program A. So he types in program A.exe, whatever, right? So the boot program will look at where program A is and jump to that memory location and start executing. And when program A is done, hopefully, it gives back control to boot, right? And then, so what do you see the problem here by doing it this way?
Problem is, I mean, you executed one program and went back to the original location.
Yeah. So
Okay, problem in the sense it's
you have to wait for
program to get completed.
to finish before you can do other stuff, or you can pause the program. And you have to make sure that the program is not malicious, right? What if the program B just refuses to give back control? Now you just
got stuck there.
got stuck there, and you have to reset the computer or reset the matrix, I guess, to regain control. Right? So there's no safeguard here. If the program misbehaves, then that's it. Who knows what it can do? Right? So is that it? Right? What if we have tens of potential programs that we may want to run, not just two? What if we want to run multiple copies of program A at the same time? Right? If you have your computer, you may have multiple copies of a program like Notepad at the same time. Right? This previous arrangement will not work in this case, right? So how exactly do your laptop or desktop computers and your smartphone accomplish this? Do they have many CPUs? No, at most they have 4. Right? For simplicity's sake, they usually just have 1. So this is how it works. Right? So you still have your boot program, so it's the bootloader. Basically, the first thing that the CPU executes when it power cycles. Right? So what a general purpose computer does when it boots, it loads the operating system. Right? You know, the BIOS. Right? It even lets you choose in the BIOS, like where you want to load the operating system from. Is it a thumb drive? Is it a hard drive? Which hard drive? Things like that, right? So this is what the BIOS is in the non-volatile memory, somewhere in flash or EEPROM. So it asks the user, okay, where do you want to boot from? Let's say we want to boot an operating system. We call it the Fritz OS in this case, right? Let's say you want to boot it from the hard disk drive somewhere else. Boom. All right, so it tries to access the hard disk drive and then load the OS to memory. After it's done, it hands over control to the OS. What do I mean by handing over control to the OS? What do you think it means? Everything is memory mapped, right? So the boot has memory location. The OS now has memory location in RAM. So basically, you just load the address of the OS to the PC. So it starts executing the operating system. Right. Now, let's say the operating system asks you, hey, what do you want to do now? Like, I'll give you a terminal, so if you want to do anything. So we tell the OS, hey, load program A. Okay. So now program A is loaded to memory. So when the program gets loaded to memory and getting ready to execute it, it's called a process. Right? So there's a distinction between program and process. A program is basically just a collection of instructions for the CPU. A process is a copy of the program that has some other context, some states, right? Which you will see later. Why the distinction?
Why is it running in the main memory now? process A.
Good question. Why not just execute off flash memory?
That's what the program is actually being stored in the non-volatile memory, right? So how come it's processing in main memory now? Because the OS is there.
How do you execute programs on your desktop computer?
So obviously based on memory mapping. Obviously you go tell the CPU go there and perform certain instruction, right?
Yeah, but when you double-click notepad.exe, what happens afterwards? Think about it. Does it execute those instructions off the hard drive? No.
No.
It loads it to RAM first, right? Because RAM is much faster.
Yes.
And sometimes you want multiple copies of the program, right? So you want to load the programs first as processes in the memory and then execute.
Okay.
Right? In some controllers, it's possible to just execute off flash memory, right? Because the CPU is much slower. But if your CPU is 2.4 gigahertz, right, so it's just you want to load it to faster memory location. Now the OS to start executing, right? So it jumps to process A, it's running. Now what happens if process A is waiting on I/O? Let's say it's waiting for user to press a key, right? Can we, like when process A is waiting for I/O, can we use the CPU cycles more efficiently?
You can run another program or
Yeah, right.
You can execute other programs while you are waiting.
Wouldn't it be nice if we can actually put that process to sleep and get another process to run, so you don't wait for that I/O and do nothing, right? So yes. So let's rewind a little bit. Okay, process A is running, and then we said to Fritz OS, wait a second, give me back control. And since the OS has higher level of privilege, it can actually interrupt the other processes and regain control. Right? You know, if you go to test manager, you can end process, whatever. Right? So the CPU needs to support this level of privileges, where you can actually have the OS having higher level of privilege. Now you go back to the OS, we tell it to load program D. Now we have two processes ready to be run. So let's continue. So process A is running again. Now, when the process A is waiting for I/O, we can make it yield the CPU. Right? Hey, you're doing nothing anymore, right? Why don't we just take over the CPU, that effectively puts the process A to sleep, and then let process D does its business, right? So now, instead of waiting for the I/O, you use the CPU to actually execute other useful operations.
So when the data from the I/O is available for process A,
you can interrupt the CPU and, hey, I have new I/O, and the OS can actually hand back control to it. Or not, or you can wait depending on your OS. So this task of placing processes and having each process execute on the CPU is called scheduling. This is process scheduling. Right? So basically you're time sharing the CPU with multiple processes to make sure that the CPU is minimize the idle time of the CPU. Right? So this is called a time sharing. So when you do this, you may have a single CPU, but it seems like there are multiple programs running, right? Because you switch back and forth between the processes. When one process has to wait for I/O, like keyboard or whatever, you bring other process in. Right? So we use interrupts to handle all this. So instead of waiting for I/O, we say, hey, I/O is still busy, so I'm going to kick you out. And when the I/O interrupts me, which means it's done, then I can bring you back in and then let you execute again. Or the operating system can give each process a slice of CPU time, or a time slice, right? So you don't want a process to hog the CPU until it gets to I/O. Sometimes you just want to switch through all these different processes, so to give the illusion that you are running multiple programs at the same time, which you will see in a bit. So the other task is when the process finishes, which means it has nothing else to do, or in the program it reaches the end of main, for example, then you free up resources so you can be reused by other processes or other things on the system. So, from the perspective of the programmer, do you have to do anything special to take account of all this new mechanism? Now you know your program can be kicked off the CPU at any time. Do you have to do anything special?
What do you mean special?
Do you have to do anything differently as opposed to when you have full control of the CPU?
Not really.
That's the idea.
Yeah.
You shouldn't, right? What about from the CPU? Like you've learned in class that the CPU has a limited set of registers. How do we make sure that the processes don't clobber each other's data, right? Because when you write a program, you just say, I'm going to use registers T0, T1, T2. Like when you get switched out, how do you know that your values are still in those registers, right? How about main memory? When you start accessing memory locations, how do I make sure that you are not overriding other processes' data? Or do you have to make sure?
Yeah, we have to make sure.
No, you don't.
No, I mean, whatever.
Not you. Like the programmer should not care,
Okay.
but the OS and the CPU needs to care, right? The idea is you want the programmer to think that you have the whole CPU to himself or herself, right? Like what about I/O? How do I make sure that I have exclusive access, right? When I want wait for keyboard, I want me to get that input from the user, not other people, and not other processes. So how do I make sure that I get that data? Right? You should not be able to. You should not change anything on your program to make sure all of this. Like it should be taken care for you. So let's answer the first question. Like, so how do we deal with the processes not clobbering each other's data? Right. So each process have a context or state. So this state is basically memory locations that you have access to, variables, registers, PC, your stack frame. Right? So these things are specific to a process. And if you're going to kick this process off the CPU, you make sure that this is safe somewhere, right? So when the context is switched, that is, the CPU pauses one process, like process A earlier, and switch over to process D, you want to make sure that all these things, the registers, the PC, and the stack for process A are safe. Because if those are lost, then you basically just reset the program. Right? Whatever progress that process had is gone. So in the OS, the scheduler, when you schedule, there's this thing called the process control block. So this is basically the structure that the OS uses to save all these things, like that. If you take operating systems class or you try to muck around with the Linux kernel and the scheduler code, you'll see how the context switch works. So let's visualize this. So let's say we have process A running, and then it goes to sleep, right? So there's a timer interrupt, and the OS says, hey, I need to let other process progress. I need to kick you off the CPU. So the OS actually needs to save the process context, the register, and everything, and loads the next one, and then it hands over control to process D. And then after its time's up, go back, the OS takes control again, do the same thing for process D, and then so on and so forth.
How does the CPU know that one program is actually waiting for something?
Because when you use I/O, you actually have to use syscall. So you have to ask the OS, hey, I want to read from terminal. So then the OS takes control. Hey, you're reading from terminal, but terminal's ready, so I'm going to put you to sleep.
Okay.
That's one way to kick the process off the CPU. Other is by time slice, right? Should we switch faster or slower, right? You don't want one process to hog the CPU, even though it's not using I/O, right? For example, when you Alt-Tab in Windows, like if you don't switch fast enough, the human user will be able to perceive it. So do you want to switch faster or slower?
Okay, good question.
Between processes.
Which fast?
Depends.
Yeah, depends.
If
So
you
that-
want interactivity, you want faster. Can you imagine if the context switches at 1 second? You're using your Windows computer, you want to Alt Tab to Notepad, there's a 1 second delay every time you do Alt Tab. Would that be annoying?
Yes.
Right? So you want to make sure the switches, if it's an interactive system like your smartphone or your computer, general purpose computer, you want to make it fast enough so that user can see it. Hey, it looks like everything's running at the same time. Right? So it switches the process back and forth. But why not too fast? What's the disadvantage of switching too fast? Like every other thing, there's an overhead. When you do a context switch, you save these registers, there's an overhead. Right? So if you switch too often, then all you do is switching and not doing anything useful with the processes. Right? In some cases, it pays to not switch a lot. When you are running a huge server and you're running just 2 processes at a time, and there's no point switching it back and forth. You just want that process to finish, and that's it. Cool?
Yeah.
Now, what about main memory? How do I know where other processes are putting their data? Should you know? You don't have to, right? If you have to be careful of where other processes are putting their data, it's pointless, right? You want to make sure that every program sees itself as the sole owner of the computer. So this is the second task of the OS and the CPU, the virtual memory. How do you virtualize the physical memory so you don't see, so the programmer thinks you have the whole memory, although you don't, right? So the OS and the CPU will make sure that they don't invade each other's spaces. Right, so the CPU will actually have to be augmented with more mechanisms for this to work. So those are the 2 tasks so far of the OS, the scheduling and the virtual memory. So next time we'll look at virtual memory, just the surface, because if you want to actually know the details, you should take the operating systems class, right? How and all the data structures that go into all these mechanisms and algorithms. So you should take operating systems if you're interested. But we're just touching the surface because you've been learning about the computer, like the registers, program execution, and we're moving up to the system level, how to make the CPUs more useful. Right? So, but the details, I'm just going to skim over because it's worth another class or 2 to actually see how scheduling and virtual memory works. All right, so that's the re-recording of lecture 16 in this class. Thank you to Sunil for accompanying me. So
Yeah, it was nice.
for CBS students, I'll see you tomorrow. And then, all right, have a good day, morning, or evening, depending on where you are and when it is. Goodbye.